All right, let's go ahead and get started. Before I start on the main lecture, just a couple of quick administrative reminders. Homework 0 is due on Gradescope tonight at 8 p.m. So don't forget that. And it really is 8 p.m. At 8 p.m., Gradescope will shut down. So if you've got a draft at now, submit it now. You can resubmit to Gradescope as many times as you like. It'll only remember the last thing you submit, and that's what we'll end up grading. Homework 1 will be due a week from today, again at 8 o'clock. That'll be up on the web a couple hours after class. It's ready, I just need to post it. It'll be about regular expressions and DFAs, which is what we're going to talk about today. Office hours at this point are reasonably solid. Mine may still move around a little bit just because for the first couple of weeks of this semester, we're interviewing department head candidates. But in particular, I'm going to, for the foreseeable future, I will continue to run office hours Tuesday immediately after class out there, but let me remind you, I'm not going to answer questions about homework. This is meant for higher level issues. I'm completely lost. I need help. This weird thing came up. Can we schedule an appointment to talk somewhere else? Not specific questions about the homework that's due today. I should thank those of you who have been active on Piazza for pointing out bugs in the lab solutions and pointing out bugs in the lecture notes. There was an excellent suggestion made last night or this morning about posting a Google Doc that just collects these bugs so that we have some systematic way of keeping track of them. I'm not sure why I haven't already been doing this for 15 years, but we should do it. So I will start a Google Doc and post a link to the course webpage. If you find errors in the lecture notes, if you find errors in the homeworks. So for example, somebody noticed that there was a mistake in the homework that the string in, what was it, problem 3, there's a long string of bits. You're supposed to show it belongs to a particular language. And if you go to Gradescope, when you submit, it says part A, and there's a different string there. That's the sort of mistake that happens occasionally, and we'll adjust for it by saying, if you proved something about the string in the PDF, great. If you proved something about the string in Gradescope, great. We'll take either one. So whatever work you've already done, we'll take it. We'll grade it. But that level of mistake is exactly the kind of thing that is extremely helpful to point out to us on Piazza. And if you do it on Piazza, then I can be publicly embarrassed when I don't fix it, instead of if you send me email, I'll only be privately embarrassed, which is much less powerful. Question?
So you mentioned posting homework later. There's already one up. Is that correct?
There's already one up where? Probably. I posted something to the TAs yesterday, and it's possible that Philip went ahead and posted it since the TAs thought it was okay. But there may be like one last-minute revision today. So nothing major. Any other administrative questions? Oh, one last thing. The homework 0, everybody needs to turn in their own individual homework 0 solutions, which they wrote themselves in their own words. For homework 1 and later homeworks, you can submit, groups of up to 3 students can submit homeworks. The expectation is that everything that is submitted with your name on it, you have read or discussed or something with the other members of your group, so that you are, by putting your name on it, you're certifying that you agree to let this be submitted in your name. If later something comes back and says, oh, I had nothing to do with that homework, we just split up the homework and never talked about it, that's formally an academic integrity violation because you let somebody submit homework with your name on it but didn't reflect any of your work. So it is definitely useful to split up the writing, but what I would really, really strongly recommend is each member of the group think about the problems on your own for a while, then the group meet, have some joint discussion to clear up each other's misunderstandings, make sure that discussion ends with a mutual understanding of what you're going to put in the submission, then split up again maybe to write the drafts of the various problems, and then at least exchange emails saying, this is what I'm going to submit, is this okay? Don't just say, you do problem 1, you do problem 2, you do problem 3 every week. Bye. Don't do that. I mean, the homework is there to help you practice. You're not benefiting from that practice. And as I said, by putting your name on it, you're sort of certifying you did something. So don't lie. All right. So today we want to start talking about finite state machines, or deterministic finite automata, a couple different names. So I want to start by giving a real-world example, and I apologize for starting off with an example that is relatively modern. This is this is the Pascaline. This is a mechanical calculator designed and constructed by the French mathematician Blaise Pascal in the 1500s. Okay? Each of these wheels represents a decimal digit. There's also a readout at the top of what the digits, what the settings of the wheels are meant to reflect. And the way that you do arithmetic with this device is you take a stylus, one of these, not an Apple Pencil, they didn't have those yet, but some sort of stylus, and you stick it into the gaps in one of those gears, and you move the gear either clockwise or counterclockwise to increment or decrement that particular digit. And under the hood, inside the machine, there's complicated mechanisms, here we go, to execute carries. So if you have one of the wheels that's set to 9 and you turn it one step clockwise, it'll automatically carry by adding 1 to the next digit. And if that's a 9, it will carry again to the next digit. And that's a 1 that will carry again to the next. So this was one of the earliest mechanical devices that could execute these carries automatically. Now, there was a similar mechanism, I believe, for doing borrows if you want to do subtraction, but it was a little bit clunkier because really it was just meant to do addition. It's literally just a mechanical adding machine. All right, so if you're into this sort of thing, if you're a mechanical engineer, you want to think about gear ratios and stuff like that, this is a fantastic example of a cleverly designed mechanical part meant to carry out this abstract mathematical operation of carrying a 1, right? And it was actually, quite a significant achievement at the time. In no small part because these parts have to be machined with considerable accuracy. And as I said, it was the 1500s. Now, the thing to keep in mind about this is a finite state machine. Okay? The state of the machine is sort of a description of, it's out of the box. I know how the machine is built, but in order to understand how everything is configured, you need to tell me what is the position of this gear, what is the position of the 1/100th gear, what is the position of the 1/10th gear, what is the position of the units, tens, hundreds, thousands, 10,000s, and 100,000s gear. So if you tell me the positions of those gears, I now, in principle, know everything there is to know about the configuration, where the gears are internally, everything about the machine. So I can describe the machine by writing down, for that example up there, a six decimal digits. For the drawing further down, 8 decimal digits. There are several different versions of this machine built. And so the machine, at least for purposes of understanding it functionally, has either 1 million states or 100 million states. As opposed to other machines that people might have built in the 1500s, made of levers and pulleys and wheels, where the state of the machine is how much rope is there between me and the first pulley. It's a continuous quantity. What is the position of this lever, of this balance? How much water is in this bucket? These continuous quantities that go into describing the configuration of a machine don't show up here, at least functionally. Now, of course, in real life, you can have the gear being sort of halfway in between, but that's not kind of a legitimate state. It doesn't mean anything. You're just going to jam the machine if you try to do that too much. So at least for purposes of its designed, intended functionality, there's a finite number of states here. There's also a finite number of things that you can do to the machine to change its state. So for each of the wheels, I could say for wheel number, or for the 100,000th wheel, I can move it 1 step forward or I can move it 1 step back. And for every possible input to the machine, wheel J forward or back, that takes the machine from some state to some other state. So some 8-digit number, and if I increment the tens digit, the state of the machine becomes the old number plus 10 mod 100 million. Okay. And then finally, in this particular example, this is a finite state machine that computes a function. The state is in some sense also an output, but you could imagine something simpler. The modern metaphor would be I stick a light bulb on the end, but as I said, this was the 1500s. So I don't know, maybe there was a little flag sticking up on the side, and whenever the wheels happen to be in the positions that represent a prime number, the flag goes up. And whenever the wheels happen to be in a position that's a complex number, the wheels go down. The flag goes down. Okay, it didn't do that, but maybe even or odd, it could have done relatively easily. So you can imagine a sense of some states are quote unquote good, and some states are quote unquote bad. And so if you did that, then you could say, okay, if I start the machine at all zeros, and I put in a sequence of numbers by, okay, first change the units digit, then the tens and the hundreds, then the thousands, then the next number, tens, ones, tens, hundreds, thousands, 10,000s, through the entire sequence of digits, and then look to see, is the flag up? And say, oh, that sum of numbers was, I don't know, bigger than 1 million. If the flag is down, okay, that sum of numbers was less than 1 million. I owe the king taxes, or the king owes me taxes, haha, very funny. And so this is the idea of what a finite state machine is. Part of the reason I'm showing this to you is to get across the idea that when I say finite state machine, the word machine is not merely a technical term of art disconnected from its normal everyday meaning. It really is built on the idea of a device that was machined. It was put together out of levers and gears and wheels and mainsprings and so on. Now, the Pascaline had, several more modern successors. You might be somewhat more familiar with this device on the left. This is a modern reconstruction in the Computer History Museum in Mountain View, California, of Charles Babbage's difference engine. Now, the difference engine could do quite a bit more than what the Pascaline could do. Among other things, it had something that you might refer to as memory. It was really set up to do, if you've taken 357 or 450, You might remember something about doing integration by forward differencing. That's what this machine did. You could actually program it by setting certain pegs in certain places. It actually had a printer, so you could spit the output out. It wasn't the same kind of input mechanism that we had for the Pascaline, where you put things in sequential. You'd add them all in at the beginning. But nevertheless, this big, complicated mechanical device lives in one of only a few sextillion states, or less than a Google states, some finite number. Each of the gears is in one of 10 positions. A more modern descendant of that still is the mechanical Curta calculator. This had little levers on the sides where you would set digits, and there was also a place to set digits in different places, and then you would turn the crank once and it would add the digits on one side to the digits on the other. And if you turned the cranks enough and did some shifting enough, it would do multiplication and division and square roots. That is how we built the atomic bomb. That is the reason why we have electronic computers, because people's wrists were getting tired. Also because Turing actually had good luck at Bletchley Park building, and other people building the first electromechanical computers. They weren't purely electrical. But literally, the Manhattan Project was the calculations were done with rooms full of people using these finite state machines in their hands. Okay, so machines. On the other hand, the other thing that I want to emphasize here is that we're not thinking about the machines as physical devices, but we're thinking about the machines as mathematical abstractions, as functions, basically. The Pascaline is a beautifully engineered device made of brass and wood and steel, but functionally, you should just think of it as it's a box I don't know or care what it's made of, where the states are 10-digit numbers, and the inputs are this digit up or that digit down. And the algorithm that the Pascaline implements was already known for millennia at the time that Pascal implemented it. People have been doing decimal arithmetic since before there were Arabic numerals. They just did it on a different type of device. These devices spring up basically in every civilization on the planet as far back as we have records for those civilizations. So you might recognize this is a standard, I believe this is a standard Chinese abacus. This thing just to the left of it is a Roman abacus from it's a reconstruction of something from the 2nd or 3rd century AD. This thing over here on the left, this is a Greek abax. It didn't have the beads fixed into the lines, but rather you would put stones down onto the lines representing, if you have 4 stones on the line, it represents the digit 4, except maybe the stone on the left represented 5, so you didn't have to carry so many stones around. This kind of counting table survived in medieval Europe well into the 20th century. So the office of the Chancellor of the Exchequer, which is UK's version of the IRS, actually had counting tables in the basement until like 1930, where they were still doing calculations by hand with counters on a table with alternating red and black squares. The word checker actually means both the thing that you write called a check and the pattern on this table. This is an Indian counting table. This is a Mayan abacus. These are Chinese counting rods being used on a counting table. The counting rods are thought to be, part of the origin of Chinese writing, actually, from, God knows how many millennia ago, where you use a horizontal rod to mean the digits 1 through 5 and a vertical line to mean a 5, except in even powers when you turn it the other way. But the same algorithms that the Pascaline introduced the same algorithms that you learned in elementary school for doing addition and subtraction and possibly even multiplication and division. Those have been in active use for millennia. Using these abstract, tables with sticks or rocks on a table, but these are really finite state machines. The counting table can be in a finite number of states. You just tell me how many stones, how many little rocks, Latin, how many calculi are on each of these lines, and you calculate by moving the rocks around. And then your input is move a rock from here to there, put a new rock down on the line, or take a rock off the line. And so you can change the state of the machine by interacting with it. Even though it's not a machine made of gears, it's something that the human being running the machine is actually doing all of the work. This, on the other hand, is much more what would be referred to as an automaton, because it runs itself. Auto, self, maton meaning think, basically. All right, so finite state machines. And so more generally, finite state machines are characterized by having a finite set of states, which I'll normally refer to as Q. I haven't been able to dig up why the states are called Q as opposed to S, even though the first person to use this formalism, whose name was Alan Turing, used the Q. I think people in mechanics tend to use the word Q as a shorthand for configuration, so maybe that's what it is. You have an initial or start state, which I'll just refer to as S, and as a mnemonic for start. For the kinds of, now let me keep going. I have an input alphabet, which I'll call sigma. This is the same letter sigma that we used for when we were talking about strings before. So for the Pascaline, the input alphabet is all pairs of tell me which wheel and tell me clockwise or counterclockwise. For the Rubik's Cube, the input alphabet is turn the left side clockwise, or turn the top side counterclockwise, or turn the bottom side counterclockwise. For the clock, the input alphabet is tick. Okay? There's an initial state, which is just some state of the device. There's a finite set of states, a clock. This is a Swiss railway clock, so it really is a finite state. The second hand moves discretely from one second to the other, to the next. And so roughly there are 12 by 60 by 60 states for this thing on the left. This thing on the right, of course, is a Rubik's Cube. It has about 19 trillion states, but again, finite. I have something called a transition function, which again, for historical reasons, is called delta. And this is a function that takes a state and an input symbol and gives you a state. For example, if the Pascaline is showing the number 42 and I increment the units digit, then the Pascaline shows the number 43. If the Pascaline is showing the number 999 and I increment the units digit, then the new state will be 1000. If the clock is showing 12:40 and 42 seconds and I tick, then it will show 12:40 and 43 seconds. If the Rubik's Cube is in this configuration and I turn the right side counterclockwise one step, then it'll be in some new configuration. And then finally, for the kinds of things that we're going to do with these machines, there's a set of so-called accepting states. So the Rubik's Cube is probably the right example to think of here. I'm going to specify You know, the set of states are the 19 quadrillion ways of scrambling the cube. The input alphabet is the set of possible turns. There's roughly 12 of them if you want to keep it simple. Six sides, each one step clockwise or counter. The transition function tells you how the cube changes. I'm going to scramble the cube and give it to you, and that's going to be your start state. And now what you're looking for is a sequence of moves that leads to the solved state. All right? So for the Rubik's Cube, generally, there's only a single accepting state unless you actually consider the orientations of those stickers in the middle. Then depending on exactly how you're counting the states, there might be more than one. But then the idea is you're going to give me a sequence of turns, and the sequence of turns is good if it eventually leads me to a solved cube. Okay? You're going to give me a sequence of numbers, and that sequence of numbers is good if it leads to a number that's bigger than 1 million. You're going to say tick over and over again and then stop. That sequence of ticks is good if the second hand is and the minute hand are at the top, so that's when I know to ring the bell. Okay? So this quintuple of things is a deterministic finite automata or a finite state machine. I don't really care which one of those you mean. Finite, in both cases, is important. I don't want any continuous quantities in here. And in particular, I want to make sure that you remember when you're processing a sequence of input symbols, the number of states that your machine can be in cannot depend on the length of the input. It's fixed, it's finite. You built it in the 1500s, or Blaise Pascal built it in the 1500s. Now, 520 years later, now we're actually going to feed it input. Okay? So finite doesn't just mean that it's not infinite. It means it's fixed in advance. It's set at compile time. It can't exceed some number that doesn't depend on how much input you're going to give it. So this is the definition. Now, obviously, there's no way that I'm going to be able to write down even these devices that I can wear on my wrist in terms of this formalism. So I'm going to really start by looking at a much simpler problem. Okay, the simpler problem is this. I'm going to give you a sequence of zeros and ones. I want you to tell me whether that sequence of zeros and ones represents a binary number that's divisible by 5. Okay? So 0, 0, 0, you should say yes. 1, 0, 1, you should say yes. 1, 1, 1, you should say no. 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1. I have no idea. Okay? That's why we have computers to figure these things out for us. Okay, so this is a program that if I let you think about it for 5 minutes, every single person in this room would have come up with a program that looks like this. Okay, so the input is my string, my word W, which I'm just going to represent as an array. And I'm going to start by initializing rem. This is the value of the number I've read so far divided by mod 5. The remainder when I divide the number by 5. Every time I read a new bit in this for loop, the number I thought I had just doubled and then I added a new bit. So what I'm going to do is take the remainder, double it, and add the new bit, and then reduce everything mod 5. Okay, so the correctness of this thing now just follows from modular arithmetic and induction. But the idea is that at all times, this variable rem stores the remainder mod 5 of the number I've read so far. At some point, my for loop ends. And then if the remainder that I have of the input I've read is 0, then I return true. Otherwise, I return false. Okay? This is a finite state machine. Okay, now, when I talk about these things being in a finite number of states, what I mean by the state is what are the values of all of the variables except I? And the reason that I want to exclude I here, this is an integer variable. It can take, in principle, arbitrarily large values. There's no upper bound on the number of values that I can have. Really, I should have written this as, while I'm not done reading the input, get the next symbol and then do this. So that's not really part of the state of the algorithm. It's just a convenient way of saying, if I'm not done, get the next symbol. The only real variable in this algorithm is rem. And if you'll notice, rem only takes values in this finite set, 0, 1, 2, 3, or 4. So this, if I think of this as the execution of this algorithm as a machine, and I could, if I wanted to, literally build a device made of Tinker Toys where I would go 0 and 1, and there'd be a little flag that goes up. This machine really only has 5 different states that it can be in. The transition function is given that I'm in a state Q. Remember, Q is one of these numbers. And I read symbol A. It's 2Q plus A mod 5. Here's the transition function right there. Okay, now, so this is a number between 0 and 4. This is either 0 or 1. The new remainder is twice the old remainder plus the new bit, all reduced down by mod 5. And then finally, the only accepting state is 0. If I happen to end, my input happens to end, and I'm in this state 0, then I'll return true. I like this input. I like this string that you gave me. If the input runs out and I'm in one of the other 4 states, and I go, I didn't like that. Okay, I don't accept. I'm going to reject this input. It's not a multiple of 5. Okay. So one way I could have written this machine down in a different form is by building this table where I have 1 row for every possible state, and then I have a column that says if I get the input bit, the next input bit is a 0, what state do I move to next? If the next input bit is 1, what state do I go to next? And in the last column, I report whether this is an accepting state or not, or equivalently, if the input runs out and I'm in this state, what should I return, true or false? Right. And more generally, you should think of all finite state machines as sort of following the following general algorithm. I'm going to have a single variable Q. This is going to be my current state. Okay. And then I'm going to have a for loop that reads through the input, and then I set Q to be the transition function applied to Q at the next input symbol. And then at the end, I'll say return true or false, depending on what's stored in this array. This is every finite state machine. This is the algorithm that it runs. Now that the 2 middle columns of this table, this is just an explicit way of writing down the transition function. Remember, a function is just, for every possible input, what's the output? The input is a pair, state and symbol. So I have a 2-dimensional table, row for state, column for symbol, and then in every square in that table, I write down the next state. So this is a different way of writing down exactly the same transition function that I specified before using modular arithmetic. Now there's a third way to specify the transition function, which is to build a graph. So in this state transition graph, this is what many people think of as the definition of a DFA, but it's not really the definition, it's just an illustration. You have a vertex, a node for each state. The start state is indicated by an arrow leading into the state, leading into the corresponding node. For every node, I have one outgoing arrow for each possible input. So in state 2, for example, I have an outgoing arrow labeled 0, and I have an outgoing arrow labeled 1. And the other end of that arrow is the value of the transition function applied to this state and the label of the arrow. So in general, the rule is that I will have, for every state Q, I'll have an outgoing arrow labeled A. Sorry, let me try that again. I have an outgoing arrow labeled A, and the destination of this arrow is delta of Q comma A. Okay? And finally, the accepting states I indicate by writing down a doubled circle. Okay, so in this particular case, the start state is the same as the only accepting state. So I have an arrow going into an accepting state. That's perfectly fine. They don't have to be different. Notice that I have some states where I would transition back to the same state again when I get the input. If I've only ever read zeros, my remainder is still 0. So the next time I read a 0, my remainder is still 0. On the other hand, if you walk through the math, if my remainder is 4 and I read a 1, then my remainder becomes 2 times 4 plus 1. That's 9 mod 5 is 4. Okay? So when you're drawing these state transition diagrams, again, this is another way of writing down the transition function that is equivalent to the math that I wrote up here at the top, and it's equivalent to the table that I wrote down here at the bottom. This is particularly convenient when the number of states is small, and is incredibly dangerous when the number of states is big. You'll see an example of that later. Okay. But it's important to remember when you're drawing the picture like this, every state has an outgoing arrow with each label. Now, sometimes you collapse. Instead of having an arrow labeled 0 and an arrow labeled 1 going to the same location, you just draw a single arrow and write 0, 1 on it. That's okay. And now, if I wanted to execute this algorithm, I want to run this finite state machine on a particular input. So let's say that my input is 1, 0, 1, 0, 0, 1, 0, 1. Okay. Actually, let me spread this out a little bit. Okay. So suppose I have 1, 0, 1, 0, 0, 1, 0, 1. Okay, so this is my input W. Here's my state. And initially, I'm going to start off in state 0. Next, I'm going to read the input symbol 1. So in the picture, I would follow the arrow from my current state that's labeled 1, and I go to state 1. In the table, I go, I'm in state 0, and I read a 1, so I go to state 1. Or I could do the math, and I would end up in state 1. Okay, so here I go to state 1. Now I have a 0, so I follow the 0 arrow from state 1 to state 2. Now I see a 1, so I follow the 1 arrow from 2 to 0. Then a 0 stays here, then a 0, 1, 2, 0, accept. Okay. Everybody understand given these, they're different ways of specifying the same object. You can just tell me what the states are, write down the transition function using math, tell me what the start and accept states are. Or you can draw a picture like this, or you can give me a table of this form where you need to somehow indicate what the start state is that's not actually shown in the table. But when you do this, you need to tell me what the states mean. So if you just gave me what's on the screen now, you would actually not get any points because you haven't told me what you're trying to do, right? So you need to actually say state Q means input so far mod 5 equals Q. All right, so you have to tell me what you're doing. This is exactly the same as when we're doing induction proofs and you tell me the reason for every step. This is exactly the same when you're writing a piece of a software library, that you document how your library functions are called and what they will do with your input. Right? This is how you tell me that you know what you're doing and you didn't just blindly copy the Wikipedia page for DFA without actually understanding things. And notice also it helps that I've named the states somewhat mnemonically, just like when you're writing code, you want to name your libraries mnemonically, you want to name your object classes mnemonically, you want to name your methods mnemonically, you want to name your internal variables mnemonically, because you're trying to communicate with another human being. You're not just doing math, you're trying to communicate that math with a person. And so it's very important to pay attention to how you're communicating with the brain inside the other person's head, not just, well, it's obvious. Even if it's simple like this, it's sort of obvious what's going on. You need to get into this habit because as soon as you leave this university and you go to Twitter or Facebook or whatever, and you're dealing regularly with bodies of code that number in the millions of lines, every little thing needs to be written down because even if it only takes 10 seconds more to figure out what this line of code is doing, 10 seconds times a million is more than your lifetime. Okay. Was there a hand up in the back? Okay. All right, so everybody kind of get this example. Strings, binary strings mod 5, need a 5-state machine. There are 3 different ways that I can describe the machine. All of them are correct, as long as I specify unambiguously these 5 components. What are the states and what do they mean? What's the initial state? What's the input alphabet? What's the transition function? And which states are accepting versus not accepting? Okay. A lot of you have seen this before, especially if you were in like a CE major. So let me walk through another example here. Now, generally speaking, when we're designing these things, we're interested in, actually let me write down a little bit, one more scrap of notation before I go on to the second example. Okay, we're generally interested in which strings does a given DFA accept. Okay, this is one question. If I show you a DFA and say, what does it accept? You should be able to answer. But it's not the interesting question. The interesting question is that I need to design a DFA to accept some given language L, right? Meaning, I'm going to tell you, I'm going to describe somehow a language, a set of strings, and I want you to design a machine that accepts every string in L and rejects every string that's not in L. Now, intuition can carry you pretty far for simple machines, but if we want to do more complicated things, and we will want to do more complicated things, we actually need to define these things more formally. So before I go on to the next example, let me actually give you the definitions here. Okay, so remember I have a machine that consists of states, an input alphabet, a start state, a set of accepting states, and a transition function. Okay, this is what a DFA is formally. And remember that the transition function takes a state and an input symbol and gives you a new state. But I want to feed this machine strings, not individual characters. Okay. So what I really need to define is a function, which I'll write with a little star here, that takes a state and a string of input symbols and returns a state. So if I say, suppose I'm in the start state, and I feed you this number 011, 0111, 0111, what state am I going to be in? Okay. So this is defined as follows. Given a state and given a string, I have cases. And what are my cases? Not what's the value for each case, but what are my cases going to be? W is empty or W is not? I'm giving you a recursive definition of a function on strings. The set Q doesn't have any recursive structure. I can't recurse on the set of states. And I can't, in fact, individual states are just blobs. They don't have any internal structure at all. But this object W is a recursively defined thing. So if I want to define a function on strings, I need to unravel that recursive definition. So I've got two cases. One is if W is empty, and the other is if W is a single character A followed by string X. Okay. If I'm in state Q and I read nothing, what state am I in? Q. So the first case in this definition, my state doesn't change. Right? If I don't read any symbols, my state doesn't change. If I never touch the gears, the position of the gears doesn't move. If I don't turn the cube stays as it is. The other one is a little bit more tricky. So the first thing I'm going to do is I'm going to transition from state Q following input symbol A. Okay, so I'm going to do this. This gives me a new state. And then I'm going to recursively start at that new state and read the rest of my input. So recursively, okay? So in this case, the recursive definition of delta star QW is delta star of some new state comma X, where the new state is my original transition function applied at Q and the first symbol A of my input. Okay. Then we say that M accepts the string W if and only if I start in state S and I transition following string W according to this recursive function, I will end up in a state that is an element of this set A. If I start at S and I transition according to W, I end in an accepting state. And then finally, the language accepted by a Turing machine is the set of all strings W in sigma star such that delta star of S comma W is in A. So this is the formal definition of what it means for a finite state machine to accept a language, or what is the language accepted by a finite state machine. What it means for a machine to accept a string. If I say a machine rejects the string if it doesn't accept it. Right? So at the end, you either accept or reject. Okay? So when I say what strings does this DFA accept, this is the formal definition of what I'm looking for. Now, if I want to communicate to another human being, now that I've told you the formal definition of what I'm looking for a particular DFA, I don't want you to write down this string of symbols because it doesn't give me any new information. If I'm given, for example, this DFA, what I want you to write down as the set of strings that this DFA accepts is strings of zeros and ones that represent a multiple of 5 in binary. Okay. Similarly, when I say design a DFA to accept a given language, what I mean is I'm going to tell you a language L, and I want you to design a machine M so that this string, this set of strings here, is L. So if I say, give me a DFA that accepts all binary strings that contain 2 ones in a row, okay, then you need to write down somehow a set of states, the input alphabet, that'll just be 0, 1, start state and accept state in a transition function, and convince me somehow that this is the set of all binary strings that contain 2 ones in a row. Okay. Now, going through a formal proof that a particular machine accepts a particular language, I actually do this in the lecture notes. It is a long and tedious exercise in induction. And really, to do it right, you have to not only tell me what language the machine accepts, but you need to tell me the language of all strings that reach any particular state in the DFA, and then you need to argue by mutual induction on all states simultaneously, doing induction on the length of the string. I will not ask you to do this. Not going to ask you for formal proofs for DFA correctness. What I am going to ask you for, and this is the reason why we're asking you for this, is tell me what this state means so that I can judge for myself whether it makes sense if going from state 2 to state 3, when I get, when I get a 1, actually makes sense. Okay, so I want you to guide me towards correctness. I'm going to give me some justification, but I'm not going to be asking you for formal proofs because we don't have that long to live. Okay, so you need to be convincing, but not formal, not with a formal proof. Okay, so let me start now with this language. Okay, I want to design a DFA that accepts all strings that contain 2 ones in a row, all strings of zeros and ones. Okay, because I've specified here that the strings have to come from the alphabet 0, 1, this already tells me the alphabet for my DFA. But I need to figure out what the states are, what the transitions are, so on. So I could approach this exactly the same way that I approached the mod 5 problem. I could say, let's write a program. And I need to make sure that when I write my program, I do it in a way that I don't have any variables except this loop counter I that can take on more than a finite number of values, more than a bounded number of values that I can write down. So this particular program has 2 variables. Found is a Boolean that says that's true if I have seen 2 ones in a row, and false if I have not seen 2 ones in a row. Last 2 is a string that represents the last 2 symbols that I've read, if I've read anything, and really I should be initializing this at the beginning to the empty string because I haven't read anything yet. On the first input symbol, it's a special case. I haven't found 2 ones in a row because I've only read 1 symbol, so I'll set the string last 2 to just be the first input symbol. Otherwise, later, I'll set last 2 to be the previous input symbol, which I just remember. In fact, I can extract it from the old value of last 2 and the new input symbol. And then finally, if at any point during the execution of the algorithm this variable last 2 is equal to the string 1, 1, I'll set my Boolean to be true. If that never happens, then the Boolean false will survive to the end. And when the input runs out, I return true if I've set this found to true and false if I haven't. Okay? So the number of states that this algorithm can be in is, well, I have 2 possible values for found, and I have 7 possible values for last 2. Epsilon, 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. So altogether, this algorithm has 14 internal states. 14. Now I can grind, 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 grind. Here's my DFA. There's my table. There's my state transition graph. Isn't it lovely? At this point, the only thing that you should be convinced of is that there is a DFA that can accept this language. This is not what you should be turning in. Now, I can explain every state. I mean, this state, f comma 1, 0, this means the found variable is false and the last 2 variables equal to 1, 0. And I just brute forced completely. I just put down 14 circles and I drew arrows between them and I moved them around in OmniGraffle until the arrows didn't overlap very much. And I put curves on them to get them out of the way of each other, and I did the best I possibly could with this. Similarly, writing down the table, I just grind, grind, grind. You can see this, for example, here and here and here are the places where I actually set things equal to true. But really, the logic of the transition function is bound up here in the code, and that would be fine. Okay, so I have 14 states, including 7 accept states, because there are 7 different ways that the states that the algorithm can be in. That if it ends in that state, I'm happy. Okay. Now that I've convinced myself that there is in fact a DFA, I really want to try to come up with something that's a little bit more reasonable. I could do it from scratch. I mean, it's actually relatively easy to design a DFA for this language from base principles. But I want to start by saying, okay, I've got this big, complicated DFA. Maybe there are things that I can do to it just to notice that I don't need all this detail. So can anybody stare at this DFA and point out something that I can just throw out? Yes? Right, so there's this state here in the middle, and there's no way to get to. And now notice what this state actually means. It means I have not ever seen the substring 1, 1, and the last 2 symbols I read were 1 and 1. You can't get into that state because it doesn't make any sense with what the meaning of the states is. So I could just take that state and throw it away. More generally, if I ever discover that I have a state that you can't get to from the start state, so-called inaccessible states, just ditch them, throw them out. Okay. Anything else that you can see that might be used to simplify this? Yeah, over here. Why is that? Right. Okay, so to repeat what he said, all of these states over here are accepting states. Once I've already found 2 ones in a row, I don't have to keep track of anything else. Right? I'm just transitioning from one accept state to another, but I already know by the time I get to this state T11, I am going to output true. If I wanted to compute some other function that put the accept states in different places, then okay, like I want to know, does the string end with a 1-1? I would put the accept states in different places. But because of the way the logic works out, once I see a 1-1, this true variable is always going to be true, which means no matter what I do, I'm going to accept, which means there's no point in keeping track of the finer distinctions between the other states. All of these things can just be collapsed down to this one state. Okay, so let me maybe do this a little bit more. This is all redundant. Likewise, this is redundant. Okay, so as long as I just change that little thing to 0, and probably I ought to change the name of the state as well. So really, I should just call this state T. I don't really, I have seen the ones. That's good enough. Okay, anything else? Turns out there are other things that one can do. So if you notice, for example, this state F1 and this state F01. Now I claim that those 2 states are equivalent. You'll notice what happens if I transition from here on a 1, I go to the accepting state. If I transition from there on a 1, I go to the accepting state. If I transition from here on a 0, I go to the state in the middle. If I transition from there on a 0, I go to the middle. Okay, so they're not, both of them are rejecting states, and the outputs of their transition functions are identical. So for the purposes of what we're trying to do with it, these states are not really different. So I could merge those states together and send the 1 going in up there down there instead. Okay. It turns out, and we'll say a little bit more about this in later lectures, there is an algorithm that can take in a description of a DFA and find pairs of equivalent states to merge together. Right? We merged all these accepting states together, but there are other states that we can merge. F1 and F01 are the same state. F epsilon and F00 are the same state. In fact, I think F epsilon, F0, and F00 are all the same state. Okay. So I can collapse these things. But at this point, maybe we've built up enough intuition we can just build the DFA from scratch. So can anybody suggest how to build a DFA that accepts strings with 2 1s in a row? Okay. Okay, so I'm going to have 3 states, which I will call 0, 1, and 1, 1. Okay. These states have meanings. So can you tell me what the states mean? Okay. So let's put in maybe it'd be easier if we put the transitions in first. So in the back. Okay, the right way to say this is last symbol, if any. was 0, and we haven't seen a 1, 1. Okay? This one is the last, sorry, let me do this the easy way. Copy. Paste. The last symbol was a 1, and I haven't seen a 1, 1. And this one is, I've actually seen a 1, 1. Okay? So, what is my start state? 0. Actually, I should also erase this. Right, the if any is accounting for the fact that I could be in here in this state, even though I haven't seen anything at all. There is no last symbol. I can only be in this state if I have actually read a 1. Okay? So if I read a 0, if I read a 0 in state 0, I'm going to end up back where I started. If I read a 1 in state 0, I'm going to go to state 1. If I read a 0 in state 1, I'm going to go back to state 0. If I read a 1 in state 1, I'm going to go forward to state 11. And then in state 11, no matter what I read, I'm going to stay in state 11. This is a full credit answer. The drawing specifies the states, the starting state with a nice little arrow, the accepting state with a double circle, the transition function, because every state has an arrow going out labeled 0 and an arrow going out labeled 1. And you tell me what the states mean, so I have some guidance to verify the logic behind the machine. Yes? Okay, every state, every symbol, you have to tell me what to do. Right? So if I'm in this state and I read a 0, you have to tell me what to do. I'm sorry? You're building, so I want, distinguish between the instructions for building the machine and what the machine's purpose is. The machine's purpose is find strings that contain a 1, 1. And so what you'd like to do in your algorithm is the moment you're in this state, you just say return true. But that's not how finite state machines work. The finite state machine has to consume all of the input characters, which means as I turn the crank and feed the input characters in at the top, if there's not an instruction for what to do in this state when I read a 0, the machine explodes, taking out the entire town and your 374 grade with it. Okay? You have to tell me what to do at every state for every symbol. In this case, it's pretty simple. No matter what I read, I stay where I am. Yes? So this answer is technically correct, provided you give me documentation of what the variables found in last 2 are. Everything is specified. Everything is clear. I can do spot checks to see that the tables are correct and the transition functions are correct. Unless the grader gets tired, and then they're just going to say too long. Okay, so remember that the graders for homework have to grade about 150 of these for each problem, and for exams we have to grade about 300 of them. And for exams, you probably have about 10 minutes to do this. So if this is what you're tempted to write down, think a little bit harder so you can save some writing time at the end. Because you're writing something like this, especially under time pressure, is very, very likely to make a mistake. Those of you who've been reading the lab notes and the lecture notes carefully understand how easily one can make mistakes. This is a lot harder to get wrong. Okay. so let's see. Maybe we can do in the last, no, I'm about to commit a cardinal sin. I was about to say, maybe we can do something else in the last 5 minutes. How often does that work? Never. The point that the professor says, oh wait, I'll do just one more thing in the last 5 minutes, you know that's going to take 20 minutes. So I'm not going to do it. Yeah, question. Let's hang out. Wait. Let's wait until people have some questions before we start making a lot of noise. Yeah. Okay, so this is a good question. I want you to remember the distinction between an accepting state and a final state. This is one of the reasons why I use an A here instead of the industry standard F. A final state is whatever state you are in when the input runs out. In this case, it could be any of those three states. Could be the state that you end in. They're all final states. If you happen to end when you're in an accepting state, then you accept. Same with like the mod 5 thing. You can end anywhere. But when you end, if you're in state 0, then you would accept. There's a distinction there. There was another question on this side of the room. If not. Okay, thanks everybody. We'll see you on Thursday. I'll be here to answer non-homework questions for a bit.
So why would you erase the half size of the final state in the graph? Yes, that part.
So these are all accepting states. Right? Once I'm in this part of the graph, I know I'm going to accept.
Oh, you collapse all into this
I just collapsed it all into that one. So the other change I made is I added this 0.
Okay. So you're still considering all the possibilities.